Take it away, Gilda.
Thank you very much for being here. I will present a study conduct at my university, Instituto Politécnico Nacional, Campus Guanajuato in Mexico. This is a joint work with professors Carlos Domínguez, Yessica Romero, Jorge Salvador, and Pablo Vega. The objective of this study was to determine if students have an intuitive idea of continuity and if they will use this intuitive idea to continuity for solving some problem-based learn scenario, and also if this intuitive idea of continuity is related to the formal definition of continuity in calculus courses, because continuity seems to be a really complex concept, mathematical concept for them, even compared with differentials of, for example, limits, and also to analyze the level of horizontal mathematization that they show while solving the problem. For the methodology, we have 79 students participated on the students divided into 29 teams, and they have a maximum of 16 minutes to complete the task. And we were not allowed them to use technology to solve the problems. The scenario will present, the scenario will present was called the robot trajectory. And the robot trajectory asked the students to help the robot to choose a trajectory from this green point to this magenta point, first going through a polynomial path and then through a straight line. So the first question was which trajectory they think is the best for the robot and to justify their answer. Most teams choose the pink trajectory for the best trajectory for the robot, and the argument was because it was the shortest one. Also the blue, the green, and the red one were chosen, and the black one was never chosen. And some of them they say because the height on the x-axis, and also some consider that avoiding all the obstacles the robot has. For the second question, we asked the students to select the polynomial function that is related to the trajectory they choose on question 1. And some teams selected the quadratic function as the function that corresponds to the trajectory selected, especially to the pink one, which was not real. On question 3, we showed the students which polynomial function is related to each of the trajectories, and ask them if having this information make them to change their answer and make a justification of their change or not. As we can see, most of the teams decided not to change their answers. And we classify the argument they did to the justification as geometric or algebraic. And as we can see with the Fisher exact test, we have a non-significant association between changing their selected trajectory and the argument they use, and also non-significant relation with the changing their changing the trajectory with the previous trajectory selected. At problem 4, we asked the student to find the linear equation that goes from the black point to the magenta point in the trajectory they selected, and explain how to get this equation. We classified these answers as correct, incorrect, or no solution, and considering what they explain, we classified as explicit solutions or theoretical solution. And we also distinguish if they were using polynomial roots or do not use polynomial roots on the solution. And also, we have a Fisher-Stark test to tell us if there is any correlation between the correctness of the solution and the type of the solution. And the Fisher-Stark test indicated us that there's a robust association between the solution type and the accuracy of the response. And also, we can see that the majority of the teams do not give a correct solution. And also, the majority of the teams give just a theoretical solution and not an explicit solution to the problem. On question 5, we asked the students to give us the complete function for the trajectory. That means that they have to use piecewise function to give the complete trajectory. In this part, we observed that the students were not really have the correct solution, but they did a continuous function. And they do not have the tools to give the right formula for the piecewise function, but even they give like a new notation for this piecewise function they were defined that was interesting. We also contrast the correctness of the solution at question 4 with the correctness of the solution at question 5, and we find that there is a significant association between the accuracy of the responses at question 4 and at question 5. For measuring the horizontal level of mathematization, we use the period Curie levels defined by them in 1994. And with these levels also comes the idea of folding back, referring to a learning returning to early levels of understanding when they encounter difficulties at higher levels, then return to is active and constructive and helping them rebuild the knowledge to go to higher levels of mathematization. We wanted to see if there was any difference on the mathematization level between the engineering programs we have. As professors, we tend to appreciate that some of the BA programs, like aeronautics, we have students with better dealing with the math than others. But the study here showed that there's no difference between the programs and that the higher level of mathematization they achieved was 6. This is partly due because the scenario is not open enough to invite them to go to higher levels, and also because of the 60 minutes time. It was difficult that they go to higher levels with the short time. We also measure the mathematization level in terms of the explicit or theoretical responses they give. So the teams that could get an explicit solution for the problems were the teams that achieved the level 6, while on the theoretical solution, they just achieved level 5. The conclusion of the study is that we could observe this folding back process between the level of mathematization 3 and 4, that most teams attempt to construct a continuous piecewise defined function. However, most could not formulate it correctly, while some teams introduced their own notation for piecewise functions. These were often imprecise or lack of formal definition. And also no difference were observed in horizontal mathematization for academic program, for semesters, for type or arguments, or the use of roots. And the difference is observed in horizontal mathematization between explicit and theoretical solution, with explicit solution demonstrating a higher level of mathematization. This invites us to keep using these problem-based learn scenarios more often into the math courses, and also to give these scenarios more time to work on and to promote this work on the folding back process on the mathematization. And this also gives us light of the students do have an intuitive conception of continuity, but it seems like what working on the formal definition of continuity, this formal definition of continuity is not naturally associated to the intuitive perception of continuity they have. So still we have a lot of work to do to fully understand the complexity of the continuity for students. Thank you very much. If you have any questions or comments.